Welcome back. In this video, we'll be discussing homework 5.1, problem number 3. So this is from WebAssign, section 5.1, problem number 3. So I pulled this directly from WebAssign, and this goes well with continuous random variables. So the PDF or joint PDF for two continuous random variables. So here's how the problem goes. It's that two components of a mini computer have the following joint PDF for their lifetimes, capital X and capital Y. So the lifetimes of these two things depend on one another, and it's given by this joint PDF. So f of little x, little y is given by the following. So it's given piecewise, and we can see the support of the function, or where the function is non-zero, is in the first quadrant, or in other words, where the two variables, little x and little y, are positive. So given this joint PDF, we have the first question. What is the probability that the lifetime of capital X of the first component exceeds 2? So using what we've learned from the last video, this can be written as follows. So what is the probability that capital X is greater than 2? It could be greater than or equal to because X is continuous, so those sort of things don't make a difference. But to be precise, it says exceeds, so beyond 2. And we'd like to express this in the following way. So this is the probability, again, since X is continuous, is bigger than or equal to 2. Well, like before, we'd like to express this in terms of x and y. So this means that x is bigger than or equal to 2 and less than infinity. So our random variable takes on a real number, so therefore it can't be infinity, so we don't get equals. And capital Y falls on the real number line. So this is true for everything in our sample space S. And as we saw last time, this event and this event are identical. So in terms of our PDF, it looks like the following. So this is a rectangular region again, and this is the integral from 2 to infinity of x, and the integral from negative infinity to infinity of y. And what is that? Just like so. So this one's a little bit in reverse order, but the idea here is that this inside integral is actually going to equate to the marginal PDF of x. So the marginal PDF with respect to the random variable capital X. So we'll figure out so this part is very much linked to part B. But in any case, we'll go ahead and evaluate this directly. So first off, going back to the definition of our PDF, we can see it only has support in the positive quadrant. So this is still the integral from 2 to infinity with respect to y, or I'm sorry, with respect to x. But the y component, going from negative infinity to infinity, only needs to go from 0 to infinity. And our PDF reduces down to x e to the negative x multiplied 1 plus y dy. So again, I draw the inside brackets to help us understand that this inside integral will give us an expression of x after we integrate with respect to the variable y, and then integrating that expression with respect to x will then give us our final answer. And so how can we do this? Well, this inside integral is actually going to be a u substitution. So the substitution will be x times 1 plus y. So therefore, du is x dy. So I've had a chance to look at this integral, and remember from calculus 2 or from integral calculus that doing these integrals, sometimes you have to try a few different things before you see a good way to evaluate them. So in this case, it's a good u substitution because we see x dy sitting in there. We also say e to the negative u. So therefore, substituting our pieces into the following integral, we get the following. Now I'll just put a little box here to help emphasize that this is out of the way. So this is all equal to still the integral from 2 to infinity of the following. So for our bounds, we see that when x is equal to 0, what is u equal to? Or I'm sorry, when y is equal to 0, what is u equal to? Well, we substitute 0 in for y, and we see that u is equal to x. So our bottom bound is x, and our upper bound, as we let y go to infinity, u also goes to infinity, because remember, our x values are corresponding to the interval from 2 to infinity. So therefore, x is positive. And therefore, u goes to infinity as y goes to infinity, looking like the following. So for the inside, or the integrand, we can see that we have e to the negative u, x dy is the piece left over, which is just du, as follows. So what is this then equal to? The integral from 2 to infinity. This inside here is negative e to the negative u. We can see that by, this is a straightforward or direct integration. If you differentiate this, you end up with the following integrand. So this is true. And this is for u is equal to x, to u is equal to infinity, dx. So I forgot my dx terms on the end there. So what is this equal to? So the integral from 2 to infinity, and if we look at this, as u goes to infinity, this expression goes to 0. So we don't have to worry about the upper bound. And at the lower bound, we just substitute u is equal to x. And since this is the lower bound, negative e to the negative x just becomes e to the negative x, as follows. Evaluating this integral, we get x is equal to 2 to x is equal to infinity. Whoops, x is equal to infinity. And as we saw in the last expression here, we get the same expression. So as x goes to infinity, this term goes to 0. So yielding then e to the negative second when doing this difference. And that is approximately 0.1353 using a calculator or computer system. So this sort of answers us up to 4 decimal places. WebAssign, I believe, only needs 3, but going to 4 places is better be safe than sorry. So the next 2 parts will be computing the marginal PDFs from this joint PDF of capital X and capital Y. So part B says what is the marginal PDF of X, and from our problem I've rewritten the joint PDF as follows. So by definition, this is then equal to the integral from negative infinity to infinity f of x comma y dy. So our joint PDF integrated only respect to the variable y over the whole real number line. So this is actually equivalent to that first expression we considered in part A. Again, noticing that f only has support over the first quadrant. this integral reduces to the integral from 0 to infinity like so. So this is the exact same integral that we had in part A. So again, like I said, part A and part B have a little bit of overlap here. And we saw last time that the good substitution to make was u is equal to x times 1 plus y, and therefore du is x dy. So I'm going to box this again so we don't get this mixed up with our string of equations here. And as we saw, as we let u as y is equal to 0, u is equal to x. As y goes to infinity, u also goes to infinity. So this is true for x bigger than 0. Okay, so this is true for x greater than 0. So we're going to assume for now x is greater than 0, and we get the following bounds. And so what's next? E to the negative u, and we have the x dy sitting to the side here, which is our du. And from our straightforward computation, the antiderivative of e to the negative u is just negative e to the negative u. And this is for u equals x to u equals to infinity. So as u goes to infinity, this expression goes to 0. So therefore, this just is equated to e to the negative x. So we should point something out here, is that when x is greater than 0, this is true. So let's put that in actually. For x greater than 0. So that was a pretty important assumption that we made. So this is e to the negative x like so. What about when x equals 0? Or better yet, when x is equal to 0, what can we notice? Well, 0 times anything, and this expression is finite, the second term in this product. So 0 times some real number is equal to 0. And when x is less than 0, f of xy is equal to 0 by our definition. So therefore, when x is less than or equal to 0, our marginal PDF for capital X is equal to 0, giving us the final answer. So our marginal PDF is equal to e to the negative x when x is greater than 0 and 0 otherwise. So now finally, what is the marginal PDF of y? So rewriting the joint PDF for x and y again, we're just given as the following. So by definition, f sub capital Y of y, or the joint PDF, or I'm sorry, the marginal PDF, integral from negative infinity to infinity of our joint PDF, but integrated with respect to the variable x this time instead of y. This also simplifies to the integral from 0 to infinity, because again, f has support that's only in the first quadrant. So in other words, when x is less than 0, it follows that our joint PDF is 0. And so this is then xe to the just like so. So here we're assuming again that y is greater than or equal to 0. So under this assumption, we have the following. So this one's a little trickier since we're dealing with x. We're integrating with respect to x instead of y. The way to go about this is integration by parts. So last one was a nice u substitution. This one will be integration by parts. So the integration by parts is to let u be equal to x. So du is equal to dx. Similarly, the other part will be our dv, which is e to the negative x 1 plus y dx. And the integral of this expression gives us the following. V is equal to just like so. So boxing this off, we can continue our integration. So just to point out here, we are integrating with respect to the variable x, not y. So y can be thought of as a parameter or even a constant. So if we look at this expression here, the derivative of the right-hand side with respect to x, oh, forgot our negative, with respect to x is the above expression. So therefore, putting these pieces together, our integration by parts formula says that this integral up top is equal to u times v and we're integrating with respect to x. So this is where x is equal to 0 to x is equal to infinity. Subtract the integral from 0 to infinity of v du, which is then just like so. So if we look at this expression here, the first one, the limit as x goes to infinity of this expression is actually equal to 0. And that's because since y is non-negative, 1 plus y is positive. And you can show using L'Hopital's rule or whatnot that in the numerator here, that must go to 0 as x goes to infinity. So I'm not going to do that here. This expression goes to 0 as x goes to infinity. So at x equals 0, this is also equal to 0 because it's 0 multiplied by some real number divided by some real number. Therefore, this expression is 0 when x equals 0. So we can cross that off. The negative and the negative make this positive. So this becomes the integral from 0 to infinity just like so, of this expression. So integrating this expression, remember 1 plus y is just a constant. So this is then negative e divided by the quantity 1 plus y squared. And this is at x equals 0 to x equals infinity. So it's clear to see y is non-negative, 1 plus y is positive, which means that the top expression here, in fact, goes to 0 as x goes to infinity. So this is then 0. Subtract this quantity evaluated at x equals 0 is the following. Gives us this. Simplifying this expression, this is just e to the 0 power, which is then 1. Well, negative 1. And so subtract negative 1 over 1 plus y squared gives us 1 over 1 plus y squared. And again, this is under the assumption that y was bigger than or equal to 0. So this is for y greater than or equal to 0. In the case that y is less than 0, our PDF, joint PDF, is 0. So therefore, our marginal PDF must also be 0. It's the integral from negative infinity to infinity of 0, which is 0. So therefore, we have the final answer. F sub y of y is also a piecewise defined function. It is given by the following. So this is the end of this video. We computed both the marginal PDF for capital Y, marginal PDF for capital X. And notice, I just want to point out one thing, is that sometimes when you're doing these marginal PDFs, depending on your joint PDF, you may or may not pick up these end bounds. So in the marginal PDF for capital X, we did not pick up the point 0. But for the marginal PDF for capital Y, we in fact did. So that's the end of this section, and we'll wrap up the rest of section 5.1 in the next video.